Look at your hand. Right now, as you hold it before you, trillions of atoms are being held together by invisible forces we're only beginning to understand. Inside each atom, particles are dancing to laws that connect you to the birth of stars 13 billion years ago. And here's what keeps me awake at night. We've discovered that all of reality, everything you've ever touched, loved, or feared, is governed by just four fundamental forces, four cosmic strings holding the entire universe together. And we're closer than we've ever been to understanding how they're all connected, how they're all one. This is the story of the most ambitious question ever asked by our species. This is our search for a theory of everything. I've spent most of my life looking up at the stars, wondering about our place in this vast cosmos. But the deepest mysteries aren't just out there in the darkness between galaxies. They're right here in the space between your atoms, in the forces that make you possible. Every human civilization that's ever existed has looked at the night sky and asked the same question in different languages. What holds it all together? What are the rules? Our ancestors saw patterns in the stars and called them gods. We see patterns in mathematics and call them laws of nature. But we're asking the same ancient question they asked around their fires. We've just gotten better at listening to the universe's answers. When I was young, we thought we understood the universe pretty well. Einstein had given us relativity. Quantum mechanics had revealed the bizarre world of the very small. But here's what troubled the greatest minds of the 20th century. These two pillars of modern physics, as beautiful and accurate as they are, don't talk to each other. It's as if the universe speaks two completely different languages depending on whether you're looking at galaxies or at atoms, and that can't be right. The universe doesn't contradict itself. Reality is one thing, not two. So somewhere, somehow, there must be a deeper truth, a unified explanation that brings it all together. Let me tell you about the four forces, because understanding them is like learning the alphabet of existence. First, there's gravity, the force you feel right now, pulling you gently toward the center of the earth. It's the weakest of the four forces, but it has infinite range, and it never gives up. Gravity is what keeps your feet on the ground, what keeps the earth orbiting the sun, what holds galaxies together across millions of light years. It's patient, persistent, universal. Then there's electromagnetism, the force behind every light you've ever seen, every thought you've ever had. The electrical signals in your neurons, the chemical bonds in your DNA, the light from the screen you're watching this on, all electromagnetic. It's billions of times stronger than gravity, but it comes in positive and negative charges that usually cancel each other out. And then there are the two nuclear forces, strong and weak, working at distances so small we can barely imagine them. The strong nuclear force holds the nuclei of atoms together, overcoming the electromagnetic repulsion between protons. Without it, every atom would fly apart and you couldn't exist. The weak nuclear force governs radioactive decay and plays a crucial role in how stars shine. It's what allows the sun to convert hydrogen into helium, releasing the energy that makes life on Earth possible. These four forces, working across scales from smaller than atoms to larger than galaxies, are responsible for absolutely everything that happens in the physical universe. Every sunset, every heartbeat, every supernova, four forces. That's it. But here's the beautiful thing that physicists discovered in the 20th century. These forces aren't as separate as they appear. In the 1960s and 70s, we realized that electromagnetism and the weak nuclear force are actually two aspects of a single electroweak force. At high enough energies like those that existed in the first fraction of a second after the Big Bang, they're indistinguishable. They're unified. This wasn't just a guess or a philosophical idea. It was proven mathematically and confirmed by experiments. Scientists Sheldon Glashow, Abdus Salam, and Steven Weinberg shared the Nobel Prize for this discovery. They showed us that the universe was once simpler than it is now. As the cosmos cooled after the Big Bang, this unified electroweak force split into the two forces we see today, like water freezing into ice, changing form but not essence. This discovery did something profound to physics. It showed us that unification isn't just possible, it's real. The forces can merge. And if two forces can become one, why not all four? This is where the dream of a theory of everything really begins, with this glimpse of a deeper unity beneath the surface of nature. Einstein spent the last 30 years of his life trying to find it. He wanted to unify gravity with electromagnetism to show that they were two faces of the same geometric reality. He filled notebooks with equations, searching for the pattern. He died without finding it. But his failure taught us something important. He was asking the right question. but we didn't yet have all the pieces of the puzzle. And didn't have all the pieces of the puzzle. The problem we now understand is quantum mechanics. Einstein's theory of gravity, general relativity, describes gravity as the curvature of space-time. It's geometric, elegant, continuous, but the other three forces are quantum mechanical. They work through the exchange of particles, through probabilities and uncertainties, through a fundamentally grainy, discrete reality. When you try to apply quantum mechanics to gravity, the mathematics explodes into infinities. The equations stop making sense. It's not that we're bad at math. It's that we're missing something deep about how reality works. This is where string theory enters the story, and I want to be honest with you about what string theory is and what it isn't. In the 1980s, physicists proposed a radical idea. What if the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy? Imagine each electron, each quark, each photon as a different vibration pattern of an incredibly small string, like different notes played on a cosmic violin. The mathematics of string theory is beautiful and strange. It requires extra dimensions of space beyond the three we experience. It predicts the existence of gravity naturally, which is extraordinary. For the first time, we had a framework where gravity and quantum mechanics could potentially coexist. But here's what I need you to understand. String theory is not proven. It makes predictions we cannot yet test with our current technology. Some versions require 10 or 11 dimensions of space. The strings themselves, if they exist, are so small that we need particle accelerators larger than our solar system to see them directly. Does this mean string theory is wrong? No. Does it mean it's right? Also no. It means we're at the frontier, at the edge of what we can know with certainty. And that's an uncomfortable place for scientists to be, but it's also where all great discoveries happen. We're in the fog, searching for solid ground. There are other approaches too. Loop quantum gravity attempts to quantize space-time itself, making the very fabric of space and time grainy at the smallest scales. Some physicists explore ideas about emergent gravity, suggesting that gravity isn't fundamental but arises from deeper quantum information. Others work on theories with extra dimensions, with multiple universes, with mathematical structures we're only beginning to understand. The landscape of theoretical physics today is rich and diverse, full of possibilities. But here's the truth we have to face with intellectual honesty. We don't know which path, if any, leads to the answer. Now, you might be wondering, why does this matter? Why spend billions of dollars and countless human lifetimes chasing after abstract mathematical theories? Let me tell you why this matters to you right now, in your everyday life. Every technological marvel you take for granted, from the smartphone in your pocket to the GPS satellites guiding you home, exists because someone once asked a purely theoretical question about how nature works. Quantum mechanics, which seemed utterly useless and bizarre when it was discovered, now underlies all of modern electronics. General relativity, Einstein's theory of gravity, is essential for GPS to work accurately. The equations we use to unify forces led directly to technologies like MRI scanners that save lives every day. But beyond practical applications, there's something deeper at stake. We are a way for the cosmos to know itself. You are made of atoms forged in the cores of dying stars. The calcium in your bones, the iron in your blood, the oxygen in every breath you take. All of it was created in stellar furnaces billions of years ago. And now, those atoms have organized themselves into a pattern complex enough to contemplate the very forces that made them possible. When you think about the theory of everything, you're not thinking about something separate from yourself. You're thinking about the deepest rules of your own existence. The search for a theory of everything is really a search for our origin story, written in the language of mathematics. It's asking, why is there something rather than nothing? Why does the universe have the particular forces and particles it has and not some other combination? Why are the constants of nature, like the strength of gravity or the charge of an electron, precisely what they are? If gravity were just slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together and chemistry would be impossible. The universe seems fine-tuned for our existence, and a theory of everything might tell us why. Some scientists propose the multiverse, that our universe is just one bubble in an infinite foam of universes, each with different laws of physics. We happen to live in one where the laws permit life, because in all the others, there's no one around to notice. Other scientists find this explanation unsatisfying, a kind of cosmic shrug. They believe there must be a mathematical reason, a logical necessity why our universe is the way it is. These are profound questions that touch on philosophy, on meaning, on the biggest why questions we can ask. I want to share something personal with you. After a lifetime of studying the cosmos, what strikes me most is not how much we know, but how much we still don't know. Dark matter makes up most of the mass in the universe, and we don't know what it is. Dark energy is accelerating the expansion of the cosmos, and we don't understand why. We don't know how the Big Bang started, or if time itself has a beginning and an end. We don't know if there are other universes, or if our universe is all there is. The theory of everything, if we ever find it, will answer some of these questions, but I guarantee you it will also open up entirely new mysteries we haven't even thought to ask about yet. And that's okay. That's more than okay. That's wonderful. Because the joy of science isn't just in the answers, it's in the search itself. It's in the moment when you realize that a pattern you've been staring at for months suddenly makes sense. It's in the collaboration between minds across continents and generations, building on each other's insights. It's in building on each other's insights. It's in the humility of admitting when you're wrong and the courage to propose something radically new. Every equation we write, every experiment we perform, every observation we make is a conversation with the universe. And slowly, patiently, the universe answers back. The closest we've come to a theory of everything is closer than Einstein ever got, but we're still not there. We've unified two of the four forces. We have candidates for the full unification that are mathematically consistent. We have experimental evidence pointing in certain directions. Young physicists today, working in laboratories and offices around the world, are asking questions that would have seemed like magic to me when I was their age. They're using quantum computers, artificial intelligence, gravitational wave detectors, particle accelerators more powerful than ever before. They're standing on the shoulders of giants, and they can see further because of it. What would a true theory of everything look like? Honestly, I don't think anyone knows for certain. It might be a single elegant equation that fits on a t-shirt. It might be a complex mathematical structure that takes years to fully understand. It might involve concepts we don't even have words for yet, but whatever form it takes, I believe it will be beautiful. Because every time we've uncovered a deep truth about nature, from Newton's laws to Einstein's relativity to quantum mechanics, the underlying mathematics has possessed a kind of austere beauty, an economy of expression that feels almost purposeful. There's a famous quote often attributed to Einstein. The most incomprehensible thing about the universe is that it is comprehensible. Why should a universe that doesn't care about us be understandable to us? Why should the human brain evolve to avoid predators and find food on the African savanna be capable of grasping the laws governing black holes and quantum fields? The fact that mathematics, an invention of human minds, describes reality so perfectly is itself one of the deepest mysteries. A theory of everything won't just unify forces. It will have to explain why the universe is mathematical in the first place. I'm often asked if finding a theory of everything would mean the end of physics, the end of discovery, and my answer is always the same: absolutely not. Even if we understand the fundamental laws completely, we'd still have to figure out how those laws give rise to the incredible complexity we see around us. How does the theory of everything explain consciousness? How does it explain the emergence of life from non-life? How does it explain why snowflakes form such intricate patterns, or why galaxies spiral the way they do? The fundamental laws are like the rules of chess. Knowing the rules doesn't mean you know all possible games, all possible strategies, all possible beautiful combinations. Reality is an infinite chess game, and we've barely begun to explore its possibilities. Here's what I believe in my bones: we will find it. Maybe not in my lifetime, maybe not in yours, but someday a young physicist will have an insight that brings it all together. They'll see the pattern that everyone else missed. And in that moment, everything we know about the universe will shift into a new coherence, like a kaleidoscope turning to reveal a hidden symmetry. And then we'll look back and wonder how we ever saw it any other way. That's how scientific revolutions work. They're obvious in retrospect, impossible to see before they happen. But until that day comes, we keep searching. We keep questioning. We keep following the evidence wherever it leads, even if it takes us to uncomfortable or unexpected places, because that's what it means to do science. It's not about certainty. It's about curiosity. It's not about having all the answers. It's about asking better and better questions. And every question we answer reveals a deeper question waiting beneath So when you look at your hand again, I want you to see it differently. See the electromagnetic forces binding your atoms together. See the nuclear forces in every nucleus holding back the chaos. See the gravity that connects you to the earth and the earth to the sun and the sun to the galaxy. See the quantum uncertainty that makes chemistry and therefore life possible. You are a temporary arrangement of stardust held together by forces we're learning to understand, animated by mysteries we're still exploring. You are a question the universe is asking itself, and the search for a theory of everything is our search for the answer. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. And in seeking to understand the fundamental forces that make us possible, we're participating in the universe's own self-discovery. That, to me, is the true meaning of the theory of everything. It's not just physics. It's philosophy. It's poetry. It's our cosmic coming of age. We're closer than we've ever been. And the view from here is extraordinary.